Hi everyone, my name is Ben Oler. I'd like to welcome you to today's webinar from Asylum Research, an Oxford Instruments company. Our topic today is Piezoresponse Force Microscopy. This is actually our second session this week. On Monday we presented an introduction to PFM. Today we're going to be building on that foundation and talking about some more advanced topics at the forefront of PFM research. I'd like to welcome back Dr. Sergei Kalinin from Oak Ridge National Laboratory, who joined us on Monday and is here again today. And from Asylum, we have Dr. Roger Proksch as co-presenter. Dr. Kalinin is the director at the Institute for Functional Imaging of Materials and theme leader at the Center for Nanophase Material Sciences at Oak Ridge National Labs. Dr. Kalinin has published over 400 scientific papers, is a co-inventor on more than 10 patents, and has received numerous awards and honors for his research. His research interests are focused on the scanning probe microscopy of electromechanical, ferroelectric, and electrochemical phenomena, and the development of big data, deep data, and smart data approaches in imaging for design of new energy and information technology materials. Dr. Proksch is president and co-founder of Asylum Research. He has been active in AFM development and research for more than 20 years and has contributed extensively to the fields of PFM and nanomechanics. Please feel free to ask questions during the webinar. You'll see a text box in the interface where you can enter these. We'll collect the questions, and Sergei and Roger will address as many of them as they can, as time allows, at the end of the presentation. If we're not able to answer all of them, we'll be sure to get back to you individually. Today's webinar is just one of several planned for the year. If you don't want to miss these, please go to our website, www.asylumresearch.com/webinars, and you can email us to subscribe to our mailings. Also note that the webinar today will be recorded and available for viewing later. Simply follow the same link you were sent in the registration confirmation email. If you missed the session on Monday, I highly recommend checking out that recording too. Okay, so let's go ahead and get started. Roger will be speaking first.
Hello everyone, and thanks Ben for the introduction. I'm going to outline our webinar for today. First, Sergei will tell you a bit about some advanced hysteresis and multidimensional spectroscopies he's been working on with his group at Oak Ridge. He will also introduce a technique called Electrochemical Strain Microscopy, which is a new way to look at ionic materials, energy storage materials, and so on. After he is done, I will discuss quantifying PFM, and by quantifying I mean actually trying to accurately measure the sort of functional parameter, so the piezoelectric coefficient with the scanning probe microscope. With that, I will pass you on to Sergei Kalinin.
Thank you very much for the introduction, Ben. So today I would like to talk about the application of PFM to piezoresponse force spectroscopy. So meaning rather than just visualize ferroelectric domains, we're going to see how we can use this method in order to study the polarization switching at each given location in detail. So imagine that we put our AFM probe in contact with the surface and start to apply these rectangular pulses which are with increasing and then subsequently decreasing magnitude. So on top of these pulses, we are going to apply the sinusoidal waveform, sort of something that we normally do in the PFM. So let's see what's going to happen inside the material. Let's assume that in the beginning our sample is polarized in one direction. So in this case, we clearly have a saturated PFM signal. If we apply a bias pulse, we will nucleate a ferroelectric domain below the tip, because by definition in ferroelectric, polarization is actually switchable, and the electric field under the tip will be extremely large compared to the macroscopic analog. So in this case, the response from this domain and the surrounding matrix partially compensate each other, so our overall PFM signal changes, and we'll see it as an inflection point in the dependence of signal on the applied voltage. If we increase the bias, our domain grows, and at some point the response from this domain and the surrounding matrix will compensate each other. So then our overall piezo response is 0, and this is what we call a coercive bias. If we keep increasing the bias on the tip, the domain will continue growing, and at some point the domain would be larger than our probing volume in PFM, then our response saturates. If we go in the opposite direction, typically nothing happens until we change the polarity of the bias, and then we start nucleate and grow the domain on the opposite polarity, almost like a Russian doll. And if we repeat this process, we basically start to see the hysteresis loop. So in this case, we induce local bias-induced transition of the material. In ferroelectric, it tends to be reversible. So ferroelectric is a perfect model system for this. And this approach can be extended for more complex systems, as I will illustrate in the brief introduction to the electrochemical strain microscopy. Now, let's consider how this local hysteresis loop relates to the macroscopic hysteresis loops. Shown on this slide is the example of classical macroscopic piezoresponse loop on the bismuth ferrite film. So you can see that for small bias, the hysteresis loop is closed. For larger bias, it starts to open up, then it opens up more, and then it opens up and saturates. And we know that in this case, the hysteresis loop is the result of multiple domains nucleating, growing, and interacting with each other. In comparison, this is the example of the local hysteresis loop obtained using the PFM. And qualitatively and almost quantitatively, it behaves exactly the same way as the macroscopic loop. So for small bias window, nothing much happens. For larger bias window, the loop opens up and then it opens up and saturates. And even the width of the loop for the macroscopic case and local case are almost the same. So it's 8 versus 12 volts. However, in this case, the mechanism for the loop formation is completely different because we have only one domain forming below the tip, and in some sense we study a deterministic process of the local bias-induced transition. So the theory behind this hysteresis loop is totally different, and this is something that is very interesting to study. Now, let's look at the picture of how this domain switching happens. So this slide illustrates a very detailed and very careful study by Andrei Holkin, who imaged ferroelectric domains at each point of the switching process. So this is an extremely time-consuming experiment, and as far as I know, it was basically done only once. But it illustrates the relevant aspects of the polarization switching. So for small biases, in this case from 0 to about 10 volts, nothing happens. So we have this central grain, which remains absolutely black. At this nucleation bias, we start to form a white grain, and this grain grows with increasing bias. Notice that the grain continues growing, but the response saturates because tip is kind of sensitive only to what is below the tip. It's not sensitive to the parts of the grain very far from it. On applying the bias in the reverse direction, nothing much happens, and then in the negative biases, we start to see the formation of the black domain. So there is a very good correlation between the hysteresis loop shape and the domain shape. However, what you can also see from this image is that the domain formation is much more complex than represented by a single hysteresis loop. So domain shape is absolutely not cylindrical. It forms this protuberances, as you can clearly see in the 0.5 and 6. It forms protuberances in the different direction, as you can see in the 13 and 14. So the process of the switching is complicated and strongly affected by the presence of other grains, disorder, and so on and so forth. So the question is, how can we study the switching process in more detail? And the answer is, one hysteresis loop is actually not enough. So what we can do is acquire a hysteresis loop at each point on the sample surface, an approach that we refer to as switching spectroscopy PFM or SS-PFM. So in this case, we park the tip in one point on the sample surface, measure the hysteresis loop, shift the tip to another location, measure another hysteresis loop, and repeat this process until we perform the hysteresis loop measurements on the grid of points on the surface. So in this case, we acquire a three-dimensional data set comprised of the hysteresis loop at each location. Obviously, working with such data set is rather complicated, so what we want to do is to reduce this data to the form of the two-dimensional images that we can visualize and hopefully understand. In order to do this, we can phenomenologically describe the hysteresis loop, so introduce parameters such as positive and negative remnant polarization, parameters such as coercive bias, parameters such as the nucleation biases, and parameters such as work of switching or area under the hysteresis loop. So some of these parameters are easy to define, for example, remnant polarization, coercive biases. Parameters such as nucleation bias are a little bit more complex. If the hysteresis loop is square, then they are trivial. If the hysteresis loop is more elongated and more elliptical, then they are defined more ambiguously. If there are any parameters that you are particularly interested in based on experimental data you have, you can always tailor your analysis as you see fit. Now, let me illustrate a few examples of applications of SS-PFM to real material structures. So, the first example of such structure is the tubular structure formed by the cobalt ferrite in the bismuth ferrite matrix. So, shown in the top row is the surface topography, so you see this nice cobalt ferrite islands, and piezoresponse phase and amplitude images. In this case, you can see that bismuth ferrite is ferroelectric, as can be expected, and cobalt ferrite is not ferroelectric, as can also be expected. Now, what you can see is the SS-PFM map when we take a number of the hysteresis loops and plot the area under the loops as the color map. So you can see that the hysteresis loops are open in bismuth ferrite and hysteresis loops are closed in cobalt ferrite. So not too much surprise here. We can extract the hysteresis loop from different locations on this map, and as you can see, this is exactly the behavior. So in the red triangular dot, the loop is closed, and in the blue dot, the loop is open. Interestingly, though, if we look at the variability of the switching behavior across the surface, in some sense it is trivial. So the response loop in the black point, which is on the boundary between BF4 and CF4, is just a half loop of the BF4 phase. Because when we switch polarization, the domain can grow in the ferroelectric phase, but it cannot grow in the ferromagnetic phase. So no surprises here, and at that time it was a little bit disappointing. However, in many cases, life can be considerably more interesting. For example, shown here is the switching data on the lead zirconate titanate ceramics. And you can clearly see that hysteresis loops at some selected locations have an interesting structure. They have these very fine features. Notice that these fine features are tied to a specific location at the sample surface and not a microscope artifact. For example, the 3 points in location C are acquired with the interval of 30 hysteresis loops. So all points in C have a very pronounced fine structure. All points in D have a less pronounced but very real fine structure. And points in other locations don't have this fine structure. So the reason why it happens is obviously because the hysteresis loop tells us something about the interaction between the growing domain and the defects pre-existing inside the material. So, next question you may ask is, can we apply this approach only to the free surfaces? And the answer is no. We can also use this for ferroelectric capacitors. In some sense, it's easier because capacitors are much easier to visualize and study because you use the probe only as the mechanical contact, not an electrical bias, source of bias. And this is the example of the hysteresis loop on the ferroelectric capacitor when we acquire large 144 by 144 map of the hysteresis loops, and we can visualize the polarization switching at different locations. So analysis in this case is obviously much more complicated because when we do switching on the bare surface, we nucleate the domain only below the tip. In capacitor, the domain can nucleate anywhere, and we detect it only when it moves under the tip. What's remarkable that in many capacitors we and other groups have studied, we observe the effect of the clustering. So for whatever reason, the capacitors switch as if they're formed by effective grains much larger than the local crystallographic grains in the underlying film. So this presumably happens because of the strain interactions in the system, but this is one of those directions that still needs a very extensive studies. Now, I would like to switch gears a little bit and talk about the multidimensional PFM spectroscopies. So the first question you may ask is, why do we need to do that? Isn't the simple hysteresis loop measurements at each location enough? And the answer is not exactly. For example, if we measure something like current voltage curves, for example in scanning tunneling microscopy, in this case our complete measurement is indeed three-dimensional. We measure the current voltage curve at each location over the square grid in space. However, this approach works only for non-hysteretic measurements. So if you look at the current voltage curve I drawn, we always have one and only one value of current for a given bias. This is absolutely not the case for the hysteretic data, such as Piezoresponse. In this case, for each bias values, we can have at least two values of the response, and strictly speaking, we can have more depending on history. So from this perspective, we need to do our measurements on the two-dimensional grid, so this gives us two dimensions. We need to study the response as a function of local stimulus, so this makes it three-dimensional. However, if we want to study hysteretic phenomena, we need to study them using, for example, first-order reversal curves. So in this case, we have one more dimension. And ideally, we would want to study the behavior as a function of time, if the process is rate-controlled. So this is from physics perspective. From the scanning probe microscopy perspective, we really need to probe this behavior in the frequency domain in order to effectively utilize cantilever resonance. And lo and behold, our ideal measurements for ferroelectric switching actually has to be six-dimensional. So practically it is of course complicated, and for the time being only several five-dimensional schemes have been realized. Let me illustrate a few examples of those. So obviously let's start with the four-dimensional imaging. So in this case we can start with our switching spectroscopy PFM. So we have this rectangular waveform which is modulated, and then we apply sinusoidal modulation on top of it. So same way as I described in the few minutes ago. However, now we are going to use the band excitation rather than sinusoidal wave excitation. And in order to do it, we actually implement the four-dimensional measurements. So we measure the response at each location, both as a function of frequency, sort of the band excitation dimension, and as a function of time. And during this time, our waveform kind of follows this rectangular wave. Once we've done it, we can fit our band excitation data in order to extract the amplitude at the resonance frequency, and the dissipation as the function of voltage during the triangular sweep. So amplitude at the resonance gives us the classical PFM signal, and resonance frequency and dissipation are the new information channels that give us insight into the loss mechanisms and changes in the material structures during the voltage effects. Let's see what is the advantage of this approach. And the answer is that band excitation is optimal for studies of the rough surfaces. This is the example of such behavior. This is a honeycomb structure made out of the PZT nanovirus. So if you will, this is as rough surface as it can possibly be. So if we look at it at higher resolution, you can see that these are really small wires arranged in this very friable structure. So let's try to do the BE SS-PFM or BIPS measurements over the structure. So we create our lattice of points. We do measurements at the point which is nominally in the empty space, so practically the tip will touch by its sides the edges of this nanovirus. And we can measure hysteresis loop here, but you can see that there is a tremendous variation of the resonant frequency and very strong noise. If we do the measurements over the solid wire, in this case the response is very well behaved, and we see clear polarization switching, almost constant resonant frequency, so the response is normal. However, both for solid space and for the empty space, we can essentially measure the switching behavior, and we can map it in the two-dimensional map. So you can clearly see this switchable polarization map that shows this hexagonal motif. So the first advantage of the addition of band excitation to switching spectroscopy PFM is that it works on a very rough surfaces. An example of more complex piezoresponse spectroscopy is what we call dynamic PFM. So in this case, we perform the ferroelectric switching, but we not simply average the signal after each pulse. We actually follow the evolution of signal as a function of time. So this rainbow color scheme after each bias pulse corresponds to the time evolution of the signal. And you see that in some regions, there is virtually no evolution, so signal is set. In some other regions, you can see a very visible relaxation of the PFM signal after the bias pulse, for example, in the region which is delineated by the square. So in this case, we probe the relaxation in time after each bias pulse in the BE mode. This gives us the 5-dimensional data set. So in each point on the sample surface, we acquire this humongous data object, which is 4,000 points in time and about 100 points in frequency. So the total data set would be of order of several tens of gigabytes. However, once we acquired and process this data set, we can get very fundamental insight into the polarization switching mechanism. For example, we can visualize the switching behavior at each location at a series of the time-lapsed hysteresis loops. So in this case, the blue loop is the one measured immediately after the pulse, and the red loop is the one where we waited for a quarter of a second. And you can see that in some regions of the voltage space, the blue and red and all the between loops coincide, so there is no appreciable time dispersion. Some other regions they are not, and you can see the beautiful example in graph 3, where in the central hysteresis loop there is no relaxation, but in the intermediate loops on the left and on the right, we see a very strong time dispersion of the response. So we actually believe that this behavior is tied to the ferroelectric and ferroelastic switching. So the ferroelectric switching for small biases is instant and doesn't lead to relaxation. The ferroelastic switching, which gives rise to the snoozes on the ends of the hysteresis loop, creates a strained structure which tends to relax with time. And we start to see it reflected in the hysteresis loop shape. Again, this and many other applications of multidimensional techniques give rise to the very high veracity, very highly reproducible data sets, and they still look for the proper theory in order to explain and quantify it. Now, let me talk for a few minutes about the application of PFM spectroscopies to different material systems. And as illustrated in our first seminar on Monday, the electromechanical response is ubiquitous, and it's common not only for ferroelectric materials, but also for ionic and biological systems. And it turns out that we can actually study the ionic system using the PFM, except that in this case we don't call it piezoresponse anymore, it's electrochemical strain. The principle of electrochemical strain microscopy is illustrated on this slide. So all we do in this case is we put our tip in contact with the surface, same as PFM. We apply bias, and in electrochemical active materials, ions start moving and respond to electric bias. So they kind of have to, because if they don't move, then batteries and fuel cells will stop working. What is remarkable is that in all these materials, the molar volume, or for simplicity, the volume of material, depends very sensitively on the local concentration of mobile ions. So if the ions move, they will cause the material locally expand and contract. How significant is this effect? In fact, it is pretty significant. So in lithium cobaltate, which is the material that is used in the cathodes of batteries in your cell phones and laptops, the expansion of the lattice on lithiation is about 40 picometers. The SPM in the band excitation or dart mode can easily measure several picometers. So it turns out that by measuring surface expansion and contraction, we can study electrochemical reactions in the single unit cell over the lateral domain of order of 10 of nanometers. So compared to macroscopic current-based electrochemical measurement, this is increasing the sensitivity by about factor of million to a billion. And so this is the illustration of how the ESM works. Now, ESM have been applied to a very large number of material systems, going all the way from bona fide electrochemical materials such as lithium cobaltates or olivines to fuel cell materials to sort of intermediate cases where the surface response can be either electrochemical or ferroelectric. However, I would like to illustrate the application of ESM for the simple case of the silicon lithium cobaltate battery. So this is a tri-layer structure. We try to measure here the hysteresis loops, and we see that hysteresis loops are open only in the region when we have a fully functional structure, so both anode, electrolyte, and cathode. And the hysteresis loops are closed if we have only two or one component. And in fact, we can also perform the mapping. This slide illustrates perhaps one of the most beautiful SPM images I've seen. So this is the 1 micron map of the sample surface. The color here is the area under the hysteresis loop. And you can see that the hysteresis loop opens only on the topographic features. So we see a strong loop opening across the grain boundary. We have weaker loop opening across this wavy feature going from the center to the top left corner. And we see a number of the hot spots inside the material. And these are absolutely real. We can zoom in on the specific region and visualize it with the higher resolution, as shown on all the insets. And in fact, the top resolution here is about 10 nanometers. So the image on the bottom left illustrates the transition from the red region, where the loops are open, to the blue region, where the loops are closed, which is sharper than 10 nanometers. And we also know that this is not a crosstalk, because crosstalk changes the absolute strength of the signal, but generally does not result in the hysteresis loop opening. So this measurements of the electrochemical strain gives us insight into the electrochemical activity on the 10 of the nanometer length scales. In fact, we can go beyond that, and we can study the more complex behavior of the materials. And this is illustrated on this slide when we take these maps with the different bias window, and you can see that at 10 volts, our hysteresis loops are open on the one grain boundary, sort of start to open on another one, and there is a number of hotspot and kind of waviness within the grains itself. if we increase our bias window to 12 volts, then all of a sudden we start to see the stronger hysteresis loop opening on one of the grains and sort of smoothening of the contrast within the silicon grains. And finally, for 15 volts, we start to see that the hysteresis loops are open primarily on one of the grain boundaries and relatively less pronounced on the other. So why is it happening? The reason why it happens simply deals with the fact that transport is generally linear in driving force, and reaction is exponential in the driving force. So in this case, for low biases, the process is controlled by or limited by the reaction. At high bias, the process is controlled by the transport. And what we see is that for low biases, there is no hysteresis loop and no time relaxation. For high bias, there is a time relaxation, there is a hysteresis loop opening. And we can visualize this dependence schematically as this red and blue curve. So the onset of reaction and the slope can be different in different locations. And that's exactly what we can do using this first-order reversal curve measurements, when at each location we measure the set of the hysteresis loops. So the example of this data shown in this slide. You can see the progression at single point from closed to open loops. And at this point, these images are perfectly correlated in space because we measure them all at the same time. And we can visualize the difference between the loop opening for inactive regions, so it's kind of one slope, for the hot spot on the material surface, so you see a higher slope, and the grain boundaries, the bigger slope. We can analyze this using the multivariate statistics and show that in the first approximation it is linear behavior. And in fact, we can fit all this data at each spatial point by the line. And this is what we get. So in this case, we have a image, topography image. We see the image corresponding to the slope of the voltage behavior of the loop opening, which gives us information about the transport. And we get the image corresponding to the voltage required to activate electrochemical reaction. And lo and behold, you can see this activation voltage is pretty much the same across the grain boundaries. It's about 4 volts. At the same time, you see a drastic difference into the transport behavior. So some of the regions on these grain boundaries activate conduction easily, and some of them don't conduct really well. So obviously, this opens us an opportunity to study the reaction and transport process of very small length scale, effectively below 10 nanometers. And again, the future here is wide open. So can we study the atomic structure of these grain boundaries? What makes them more conductive or less conductive? What does the activation voltage tell us? Can we relate it to the elementary electrochemical mechanism? So these and many other questions is something that we cannot answer them now, but these are the questions that we can pose. These are the behaviors that we study in real space, and this is the field that looks for future generation of experimentalists and theorists to actually learn what do we learn with these techniques. Thank you.
Thanks, Sergei. Cool stuff. As I mentioned in the beginning, we're going to finish up this webinar with a discussion of quantifying PFM. And this is something that has its roots in the very beginning, this idea that you could measure the inverse piezo sensitivity, the D33 or D effective, as we sometimes call it, of the surface. To do this, to make this particular study, we looked at a sample called periodically poled lithium niobate. It's a uniaxial material with the polarization direction in or out of the plane. We're going to assume that this material should be more or less frequency independent, at least at PFM frequencies from 10 kilohertz to maybe a couple megahertz, certainly below the contact resonant frequency. The amplitude should be independent of that domain orientation, that we expect the same amplitude when the polarization is up or down. which means that the D33, or the effective that we measure, defined by the amplitude that we measure divided by the tip voltage we're driving at, should be the same over the two domains, and that the phase shifts across the domains should be at 180 degrees. And that was really the model, if you recall, from the first webinar, this idea that if you have a sample like that, the phase should switch between 0 and 180 degrees as the tip flies over it, and that the amplitude should be at a constant value and then go to 0 in between the domain boundaries. I can play that movie just so you remember that. Now, if you drive below resonance, of course, there's some noise and so on. So the PFM phase has some noise in it. The amplitude has some noise in it. And, of course, in real samples, the roughness and so on can corrupt that measurement a little bit, causing by the frequency shift. Our sample, as I mentioned, was this periodically poled lithium niobate. This is fairly typical phase and amplitude measurements on it. And the test I'm going to tell you about right now is that we measure an amplitude of the cantilever with a given drive voltage and at about 40 or 50 kilohertz. We then calculate the D33 with this equation here, and we're going to make histograms of that D33. So when we did that, we did it with AC 240 cantilevers, 10 of them, over the same PPLN sample, so that I guess there could be some spatial variation, but we don't expect it to be very much. The results were disappointing. So this shows you, the blue curve here shows you different histograms, and it ranges from a few picometers per volt, estimated D33, to over 30. So quite a bit of scatter. The question is, we would like to have much better precision in our measurements. The question is, what is going on? Okay, so lots of scatter. What does that scatter come from? So the first thing I thought about is maybe it has something to do with the frequency. This is a very common thing in the PFM literature, that there are different sensitivities, different effects at different frequencies. So here is a series of images. I guess it's 6 images of the phase on the top and amplitude on the bottom of a couple domains, 3 domains in this PPLN sample, all taken with the same identical cantilever, an AC 240, at different frequencies, at 40 kilohertz, 150, 190, 220, 310, and 330. The top 2 are on either side of the contact resonance. You can see the signal to noise is really spectacular there. However, the domains, the amplitude is very different on the 2 domains, unlike what we would expect. Also, the data scales below resonance and at resonance are quite different. So this frequency dependence, in retrospect, isn't very surprising, really. The cantilever is a mechanical object. It has a transfer function. By transfer function, I mean that the output, what it does, its vibrations, depend on the input frequency and amplitude. So you can think of it as a sort of a tune. These graphs here show the phase and the amplitude over the domains in the data from the previous slide. I called the red one the down domain and the black one the up domain. So the phase is positive here, and then up at about 150 it flips. There's a kind of complex structure in that. There's this transition here. And then here is the contact resonance where the phase flips and the amplitude peaks. Now, we've talked about the simple harmonic oscillator. Both Sergei and I talked about it at different spots, and it really is the sort of default model for how we think of a cantilever acting. And that simple harmonic oscillator, the transfer function for the amplitude, looks like that expression there, where this ZEM is the electromechanical strain. That's the drive driving the cantilever. The thing is, this dashed line, these dashed lines here, the red and the black curves, are the simple harmonic oscillator fit to these curves. And you can see while the curve fits okay near the resonant frequency and near the base, there's this whole intermediate range where it very much does not fit. So what that tells us, that at least for this particular set of data, that simple harmonic oscillator model just isn't quite correct. It doesn't capture all the dynamics of the system. So we need a different model. And the next model you can think about is this Euler-Bernoulli, basically an analytical model for a diving board. It's a fairly complicated model. I'm not going to go into great detail on it, but you can separate out the time dependence, the time dependent solution and the spatial solution, and you get this fourth order differential equation. I'm not going to go through the details of this. You can read about it in the references. But the thing to note about this, unlike the simple harmonic oscillator, in addition to a frequency dependence, which is in the frequency or the time dependent term, which isn't here, there's a spatial dependence. And so this x here is the coordinate along the length of the cantilever. That's very different from the simple harmonic oscillator model. So the Euler-Bernoulli equation tells us we have to care about both position and frequency. So position of the optical detector on the back of the cantilever and the frequency at which we're driving it. How do we measure this? Something called spectrograms. Spectrograms have their roots a long time ago. You've probably seen these pictures, or maybe you actually saw a live demonstration in your physics class, Physics 101 class, where you looked at solutions to the plate equation, the differential equation that relates the modal shape, vibrational modal shape of plates as a function of frequency. If you sprinkle sand as these plates are, sand on the plates as they're vibrating at their normal modes, the sand tends to collect in the nodes and reveals these beautiful modal shapes that are the solutions of that differential equation. We can use that same idea with cantilevers, and so instead of sand grains, we use photons. We scan those photons using the optical detector and the FM along the length of that cantilever. At the same time, we vary the frequency. We just sweep the frequency from, say, 0 to some high frequency. In the case I'm about to show you, 10 megahertz. And you generate these kind of pretty-looking maps of frequency and amplitude as a function of position from the base of the cantilever here up to the tip here. And you can see here's the first mode at about 300 or 400 kilohertz. Second mode, third mode, fourth mode, and so on, all the way up to a mode at 10 kilohertz with all sorts of structure in it. This movie here, I can play it in a second, is that same data in the graphic up above, but now what I've done is I've shown it as in cross-section so you can actually see the cantilever shape. Well, the amplitude shape anyway. We just went through the first resonance there. You can see this antinode that's actually visible right there. That's that node right there. As a function of frequency, we're scanning through the frequency here, and you can see this amplitude changes both as a function of that position along the length and of that resonant frequency, or of the drive frequency. So the most striking result from those the previous slide is that the response that we measure is not only frequency dependent, but it's position dependent. And by position, I mean the position of the optical spot, this incident beam on the cantilever. So where that shines on there, that position along the length determines the sensitivity. And that's really brought here. This is just a slice from that movie I played earlier. If we put our optical beam spot right here, we maybe measure, I don't know what it is, 100, call it 100 millivolts. If I move that beam just a few microns, 10 microns, 20 microns towards the base, I'm going to measure 50% of that amplitude. And so my D33 here versus here will be 50% smaller. That's a big deal, and it actually may go quite a ways as far as explaining the wide range of values we're getting with the histogram, the D33 in the PPLN sample, if you recall that histogram plot with all the different curves with a lot of scatter. So the lesson is the sensitivity for conventional AFM, at least, depends on the beam size, so the size of the beam spot on the lever, the location of that beam, and also, of course, the dynamics of the lever. And that's really what we're going to try to capture with this Euler-Bernoulli model I mentioned a little bit previously. I do have to say a quick thing about the long-range electrostatic force in the context of the Euler-Bernoulli model, and that is that most ferroelectrics do have some sort of surface charge. It may be that if there's periodic domains or very small domains, as you get above the sample, that charge more or less sort of cancels. But in many cases it does not, or at least we believe it does not. And when it does not, it is a little bit dangerous in that it acts as a background drive on the body of the cantilever. The force, it's like charge times an electric field. It's at the same frequency at the first harmonic, which is the same frequency as the piezo response signal. So there's a background in there that you can't necessarily easily get rid of if there is this surface charge. We denote that as this F cant, and this is in the model that I showed before. If we bring that up here, it's that term in the cantilever, and that is something that at least in the PPLN sample, in the results I'm going to show you on the next page, that was a term that was actually required to actually get good agreement between the experimental and theoretical values. I should also note in this equation that the piezo response, that Z electromechanical, comes in as a boundary condition on that in that equation. So you can read a little bit about it in these articles, both the spectrograms and some of the specific measurements that I'm showing here. So this next page just shows, and again I don't have a lot of time to go into this, but these are experimental spectrograms made at a DC bias of plus 5 volts, 0, and minus 5 volts. And you can see there's changes in the shape of that first resonance. So this is 0 hertz. This is the base of the cantilever along this axis, and I've only measured in this case up to 400 kilohertz. The tip of the cantilever is up here, and you can see the evolution in that structure. Specifically, probably the easiest thing to look at is this antinode line, this node, this 0 amplitude line. In the case, it evolves as a function of that applied voltage in both cases. And you can see that at least qualitative, the Euler-Bernoulli repeats that evolution really nicely. Even this little feature here is reproduced in the experimental data. Of course, since the simple harmonic oscillator doesn't include that spatial dependence, there's not much of a change in this. In this case, the interaction, the electrostatic interaction, was actually quite small. But it is notable that it was required to move to this Euler-Bernoulli model to explain that. The simple harmonic oscillator doesn't quite cut it in this case. Okay, as you can see, understanding and quantifying PFM is a bit of a challenge in that you really have to treat the cantilever as a real diving board. You can't pretend it's a simple harmonic oscillator. At least I believe that is the case when there are electrostatic forces between the body of the cantilever and the sample. I want to take the last few slides as an opportunity to show you some new experimentation we've been doing on a different way to look at this issue and this problem, and a new experimental approach we've been taking. So if you think about your Euler-Bernoulli beam and you think about cantilevers, in the history of AFM, what we really care about with a cantilever is not the cantilever. It's really this boundary condition. It's that interaction between the tip and the sample that we really are trying to measure. And that's where the physics, the material science, the biology, whatever you're trying to do, in this case, the electromechanics, that's where the action is. And so if we had a way to get to this boundary condition directly, that would be sort of exciting. And indeed, we could maybe not have to deal with some of the complications of the cantilever itself. So what I'm going to show you is a first stab at something like that. We've taken a cipher AFM, and this has a normal optical beam detector, optics that go that. There's an objective there, and so there's a cantilever down here. And then on top of that, we've added an interferometer. The interferometer is independent. It can be steered around and positioned in this plane or this plane of the sample or anything else independently. This photo shows the optical beam. It's a larger spot, and then the interferometer beam is a tiny spot. And this is an actual photograph with the cantilever, one of the cantilevers we actually use for PFM in there. And so you can see the optical beam is here. That runs an AFM as it normally would. And then this little spot here can actually go along and measure different positions. And in fact, based on my earlier discussion, we can start to look at the boundary conditions by positioning that spot at the boundaries. So the following is showing you trying to probe this boundary condition. And again, we're on PPLN. We're going to, the cantilever that we used in this case has a shape a little bit like this from the side, where the tip, you can't actually see it from the top. So what we've done is we've positioned the spot at the very tip and measured domains in the PPLN. So this is the domain image. This is a section through that. And then this is a tune going from somewhere around 0 to a little bit above 400 kilohertz, where the contact resonance is about 380 kilohertz. Now we're going to step that interferometer spot along, and you'll see as we go, there it moved back a little bit, moved back further. Now this is a pretty magical spot, right at this spot where it's right at this position centered. The domain structure looks equal. The amplitude is equal over the domains. The frequency response over a very wide range of frequency is nearly constant. It comes in at about 9 picometers per volt for this PPLN sample, and except for a couple little hiccups that have to do with maybe not positioning it perfectly over the tip, it's almost a constant function of frequency. If we continue to walk that spot a little bit closer to the base now, you see that this domain structure going from bright-dark actually goes to dark-bright, so that switches around as we would expect from that. And we go a little bit further along that, you can see that even gets more enhanced. And these tunes here show that as we add that in there, you can see this antinode goes from below resonance to above resonance. Now you can also simulate this using that Euler-Bernoulli mathematics that we've already discussed. And I mentioned that the average value is about 9 picometers per volt, but the simulations in that case come out like this, and the reproduction is quite good. So this tune here shows, again, we're revisiting the old data I showed you, the up and down domains. There's the domain images we have. These are the tunes plotted on a linear scale. You can see that there's not very much visible here because the amplitude is very small. If we take that same data and plot it on a log scale, you can see it much better. So the black and the red solid lines show the optical beam, so the normal AFM spot that most AFMs use over that range. And you can see that structure that I showed you in the very beginning of this section on quantifying it. The pink and the gray show the interferometer data over that same frequency range. So this range is from 0 to 500 kilohertz. And it's quite a striking difference. This is a pretty exciting result. The optical beam, the conventional, has something like 30 million% variation. And it's because that resonance affects it. You can't get rid of that resonant effect. But at the tip, where we're probing that boundary condition, the interferometer shows there is definitely some variation, but it's much better, mostly on the order of 15%. And we think that that variation actually comes from some instrumental drift in the interferometer. So this interferometer result suggests a new method to try to quantify our AFM response. And so we took this new method and applied it to the periodically poled lithium niobate. The new method is that you position that interferometer spot to eliminate that resonance effect. So that is putatively right above the tip position. And then at that point in time, you take an image, and you can see this image here is another image where the response over the domains is equal and looks nice and clean. And then you calculate the effective and make a histogram of it, just like we did in the original work. Now, if you recall, this was the optical beam results. We actually we applied this method over the very same domains on the very same cantilevers with the interferometer method, and the results are here. So quite an improvement. Okay, to wrap up this section of the talk on quantifying PFM, we ran into some issues with the optical beam detector in the case of the PPLN, and the spectrograms clearly showed that the cantilever shape is playing a big role in our measured response. It changes continuously as a function of frequency, and also that the spot position where you put that optical beam, the laser spot on the cantilever, controls the response. In the case of materials where there is a surface charge, you have to use the simple harmonic oscillator very sparingly, and you may actually need to turn to an Euler-Bernoulli model to take the transfer function of the cantilever properly into account. I did show you at the very end a little bit of the results from some new interferometry experiments where we've combined an interferometer with a conventional optical beam deflection sensor in our Cypher AFM. The thing that's the most exciting to me about this is that it's a way of going from arbitrary units, and that's probably overstated. I mean, you can calibrate cantilevers and optical lever sensitivities and so on, but having an interferometer in there really gets us to SI units really quickly and directly. We're sort of excited about using that in a lot of different ways, not only for PFM kinds of measurements, but other kinds of measurements. It also gives us a better understanding of the optical beam, the conventional sensor. It's a way to check our assumptions on that. It allows sensitivity and spring constant calibrations inside the microscope, and so there's a lot of kind of cool things that can be done with it. In the case of the PFM measurements, as I said, the simple harmonic oscillator model probably doesn't work all the time, at least for charged surfaces. There is this interferometry response over that tip is actually very interesting. Maybe now we have a window onto directly what is happening underneath the tip. At least in the case of the PPLN, it gave us nearly ideal results, at least when that optical interferometer is positioned properly. So we see the domain responses are almost exactly equal, and the distribution of the effective sensitivity, piezo sensitivity, goes from being very scattered to very, very tight. Okay, to finish up, I should also remind you, I think Ben did in the beginning, but we have an Introduction to PFM webinar that we put on a couple days ago. You can access that from our website. I also have to put in a plug for the Center for Nanophase Material Science at Oak Ridge. If you're interested in coming there, visiting there, and doing some experiments with some really spectacular scientists and equipment, drop Sergei a note in his email. Also, if you are looking for more information, more things to read about, please check out our website. There's also a lot of workshop materials, conference proceedings from the Journal of Applied Physics, and a few books here that you can grab a screenshot of and get on Amazon whenever you want. With that, thank you for your attention, and I will turn the microphone over to Ben Oler, who will field any questions that you may have at this point. Thank you.
Okay, thanks a lot, Roger, and thank you, Sergei. We are running kind of up against our hour that we had set aside for the webinar, but we'll go ahead and take a few questions. If you haven't submitted your questions yet, please do go ahead and type those into the question box in the webinar interface. Sergei, this first question I will give to you. In the case of both ion movements and ferroelectricity, where both contribute to the electrical mechanical response, is there a way to separate the responses that are coming from these two very different mechanisms?
So it is a very complicated and very interesting question. So in the purely ideal case, when we have the ferroelectric and the ionic material with the blocking electrodes, the answer is actually no, because the microscope detects either physical or electrochemical dipoles. Practically, however, we can separate them based on the time response. So the ions moving in the lattice have very characteristic diffusion coefficients, so they kind of move slowly. The ferroelectric polarization response is much faster. It's sort of sub-nanosecond regime. So in principle, if we can measure the response to the function of frequency, we can differentiate the ionic and ferroelectric component. Practically, of course, once we do these measurements, then our material response is convoluted with the transfer function of the cantilever. So you will primarily see the cantilever dynamics, not the ion dynamics. So until very recently, that was theoretically doable, but practically not. Now, with the advent of these interferometric methods and cantilever transfer function measurement methods, that probably becomes possible, but it's a matter of the future.
Okay, thank you, Sergei. Roger, a question for you. Is there a practical limit to the voltage that can be applied to the sample during a PFM measurement? And is this more a matter of AFM and human safety?
Yes, there is a limit. It's mostly set by the construction of the microscope itself. So you need to avoid the dielectric breakdown of, or the conduction breakdown of air, which might be something like 1,000 volts on a typical system. So that's the sort of practical limit. We chose on our microscopes to be somewhere between 150 and 220 volts just to avoid that danger. The other thing you have to be careful about, as you mentioned, is safety. And if a milliamp or something flows through your body, you can be in pretty big danger. And so you need to make sure that the metal contacts and everything else are isolated from the user of the microscope, and that's something that, of course, needs to be designed in pretty carefully.
Okay, thanks, Roger. Sergei, another question for you. Is the photodetector able to measure biological samples with piezoelectric constants of 1 picometer per volt or lower?
And that's doable. So whether the origin of the signal is piezoelectric or something more complicated like electrocapillary motion or water, we not necessarily know. But there was a series of work done by Brian Rodriguez and Kalinin when they measured the PFM signal in the biological systems such as collagen, which are of the order of 1 picometer per volt. And in many of those cases, sort of subtle effects like orientational dependence of the signal basically prove that this is a piezoelectricity, not any kind of crosstalk.
All right, thanks, Sergei. Roger, a question. In light of the interferometric results, are you saying that all previous D33 measurements are incorrect? And is that method available?
No, I'm saying it's incorrect. I'm saying that you need to be careful. And I think what we've discovered with this is that there, in the case of a sample where there is surface charge or a long-range electrostatic interaction of some sort, the interpretation of the cantilever as a simple harmonic oscillator just isn't sufficient. It really is. You really have to think in terms of both the frequency response and where you're actually probing that cantilever along the body of the people, without thinking about that, you can certainly get lucky and get the right answer. You can also get some very strange answers that don't agree with reality. I answer the second question. Right now, the interferometer is a tool that we're using in the laboratory here, so it's really a research project that we're having that I shared some results from. It is not currently any sort of product.
Sergei, one more question for you. When you talk about decoupling of transport and reaction, what is the principal difference in physics between these two processes?
Very simple. So the transport, at least in the low field regime, tends to be linear in the driving force. The reaction tends to be exponential in the local over potential. So imagine this is a case when you apply electric bias to the junction between the tip and the surface. So at very low biases, our electrochemical reaction is not activated, and basically nothing happens. Once we cross the critical bias, the reaction activates, and very rapidly we go from the regime when we are limited by reaction to the regime when whatever happens is limited by the transport of external species to the junction. So it's kind of a voltage divider when one of the resistors is linear and another is exponential. So such system will have this very sharp crossover between essentially no conduction to linear conduction. So that's how we do it.
Okay, great. Thank you, Sergei. All right, I think we'll go ahead and wrap up. We're a little over the original time that we had. I'd like to thank you all for attending. I'd remind you that we have recorded the webinar today, so if you'd like to go back and review the recording, you can just follow the same link that you were sent to log into the webinar today. You can also forward it to any colleagues that you think might be interested as well. So with that, thank you very much. I look forward to seeing you at our next webinar.